Hello and welcome to video 4 in the A1 series. In this video I'll be looking at practice questions 5 and 6, then I'll be looking at instantaneous versus average velocity and acceleration. Then we'll be having a go at practice question 7, practice question 8, and then we'll be looking at ascertaining acceleration from graphs, and then we're going to have a look at PQ 9, 10, 11, 12 and 13, and then we're going to finish off by looking at the basic laws of projectiles in one dimension. Thank you. Enjoy. Hello and welcome. We're back at A1.004 and we're just going to go through some practice questions. Practice question number 5 in the book. A straightforward question about distance time graphs. How do I know it's a distance time graph? Because it says so. It says distance up the side. We have a train leaving station A at time 0. It arrives at station B after 80 seconds. It leaves after 100 seconds, that means staying there 20 seconds, and goes off to station C, arriving at 160 seconds. There are 3 subparts to the question. Part 1, speed in kilometres per hour between A and B. So, between A and B, the distance travelled is 1,000 metres, because that's 1,000 metres. And the time taken in seconds is 80. That'll give us an answer in meters per second. So 1000 divided by 80, that's giving me 12.5 meters a second, and I immediately multiply that up by 3.6, and so the answer is 45 kilometers per hour. Part B, the distance, how far it is from B to C. What you are not going to do is start drawing a triangle or drawing an area down here and going, I need to add up this area, I need to add up that area, add the 2 together, that'll give me the distance. No, 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 no. This is a distance time graph. The distance from B to C is simply, you read it off the graph here. It's the distance difference between 1,800 and 1,000. So the answer is 800 metres. Part C, the speed from B to C. The distance from B to C is 800 metres and it took 60 seconds. So we go 800 divided by 60. That gives us 13 1/3 metres per second. We multiply by 3.6 to turn it into kilometres per hour. So that is 48 kilometres per hour. And you can see from the graph, not from my rubbishy copy, but if you look carefully at the graph in the book, you will see that this line here is just slightly steeper than this line there, because it's travelling at 48 kilometres per hour there and 45 kilometres per hour there. Okay, that's PQ5. Okay, so now we're going to go and have a look at practice question 6. Louise, this stick figure here, kicks a ball towards a wall that's 4 metres away. The ball travels at 10 metres per second on the way to the wall. It then comes back and it returns 0.9 of a second after being kicked. So there and back is 0.9 of a second. Question AI, time for ball to reach wall. Well, what do we know? We know average speed equals distance travelled divided by time. So with respect to this, we therefore, if we rearrange it, the time taken equals the distance travelled divided by the average speed. Well, we know the distance travelled, it's 4 metres, and we know the average speed because it's 10. And 4 divided by 10 is 0.4 of a second, so the answer is 0.4 of a second, which obviously means that it must be 0.5 of a second coming back. Okay, the time for ball to reach wall, answer 0.4 seconds. Part II, speed of ball on return. Well, again, it was travelling 4 metres and it took 0.5 of a second, which is a half. So when it was coming back, it must have been doing 8 metres per second. Really easy peasy. The last part, it says draw a graph. The exact wording is sketch a graph to show how the distance travelled by the ball varies with time. So we're looking at a distance time graph. Now, it doesn't say displacement time graph, it says distance time graph, I think what we can do is just like we've done before in the past, is we'll make a mark at 0.4 seconds, and that's the journey out. So there to there. This is the distance against the time, and we know that that is 4 meters. So that's 4 meters. And the gradient of this graph would be 4 meters divided by, in this case, yes, didn't go around, sorry. 4 meters divided by 0.4 is 10 meters per second, that's correct. And then we'd have another line here at 0.9, and we'd bring it down like that. And we'd have a little sort of pyramid shape or triangle shape, going up, distance 4 meters, coming back again. You could argue that you could do this out. No, I think in this case, because it's returning, I think that's the appropriate graph. So it's going steeply up and less steeply coming back. Everybody okay with that? Good. Okay, so we need to talk about instantaneous and average speed. This is a very simple distance time graph that you've seen before. We are told that in this distance time graph, the person starts here at time 0 and they weren't moving and then they start moving. Now the reality is the orange line. But if you're going to go with these curvy orange lines, you can't use Suvat equations to work stuff out. And that's why they always give you the line straight, because a straight line on a velocity time graph represents constant acceleration. If the acceleration was changing with time, you can't use Suvats, because acceleration must be constant for your Suvat equations to work, which you will come to shortly. There's a lot of stuff in the book about instantaneous and average speed, instantaneous and average acceleration. Just be aware of the fact that we tend to oversimplify things in questions by giving you these straight lines. Thank you. Welcome to PQ7. My graph isn't as good as the graph in the book. Hopefully you're all looking at the question in the book, which is much better graph paper than me. We have somebody hitting an ice hockey puck across the ice, and basically it sets off and slows down and stops 24 meters away. And the time for it to completely stop is 12.5 seconds. The question is, estimate the initial speed of the puck. It has to be an estimate because there's no straight line here. It's a bendy line. So what you will do is you'll get your ruler out and you'll find a tangent for the orange line there, and we'll say it's something like that. And then you will draw a big triangle, and at this point here, it's about 12 meters traveled in whatever that time is. And I'm looking back here, a bit less than 2.5. Possibly even 2 seconds. That could be 2 seconds where it crosses the 12. Don't look at the line on the graph, look at your tangent line that you've drawn. So let's say I think it's about 12 meters in 2 seconds, so I reckon the initial speed is about 6 meters per second. It's an estimate. Speed of the puck at 5 seconds. So look on the graph, 5 seconds when it's 18 meters away. And when it's 18 meters away, it's definitely not going as fast. You would draw a tangent. Again, you will do this with a ruler and a pencil. And then you will draw yourself a nice big triangle and do rise over run. I would say the rise is about 24 meters. And the run for my big triangle that I'm sort of drawing in my head here, 10 seconds. Probably about 2.4 meters per second, but you can have an argument about that. It's an estimate. Frankly, no one cares. Okay, they just want to they want you to show them that you know what to do. No one's going to argue too much, especially on a very poor graph like that, exactly where the tangent line is. The puck stops after 12.5 seconds. Calculate the average speed of the puck during the motion. The average speed is the total distance travelled, which is 24 meters. Divided by the time taken to actually stop, which is 12.5 seconds. Divide one by t'other on your calculator, and 1.92, 1.9. I've got 1.92 meters per second. And that's that one. Thank you. Okay, we're now going to do practice question 8 on page 16 of the good book. And we're told that somebody runs halfway around a circular track. The radius of the circular track is 25 meters. And it takes them 19 seconds to get from the start to halfway round. And we want to know, the question is, what's the average speed and what's the average velocity? Let's do average speed first. The speed is the distance actually travelled over the ground divided by the time taken. Well, we know what the time taken is, that's easy. That's 19 seconds. What's the distance around half a circle? Well, we know the whole way around a circle is 2 pi r. So let's not waste time doing that and dividing it by 2. So we know that half a circle is pi r. So the distance she travelled was pi times 25, which is 25 pi, which is 78.54. I don't like rounding too much. 78.54 metres divided by 19 seconds, 4.13 metres per second average speed. Second part, average velocity. Now velocity, strictly speaking, that's what we're going to be doing, is displacement over time. Her displacement is the distance in a straight line from where she started to where she finished. And you would agree it's 25 there and 25 there, so her displacement is 50 metres and she's taken 19 seconds. So this is 50 divided by 19, 2.63 metres per second. Any questions? All good? Thank you. Okay, so we now need to quickly talk again about acceleration. Acceleration is the rate of change of velocity. If I have a velocity time graph, going faster, levelling off, going faster slowly, the acceleration is found as the gradient or slope of the line. And because in physics, generally speaking, all these lines are straight, which means constant acceleration, all we have to do is simple rises over runs to find them. So let us pretend that that was 12 metres per second. And let's say that was 3 seconds. So what is the acceleration here? 12 divided by 3, so that would be 4 ms to the minus 2. What's the acceleration here? Altogether now, 0, because it's not changing. That'd be 0 ms to the minus 2. And what's the acceleration here? Well, not much. I'm just making these numbers up. Let's say that was 7 seconds, and over here, about double, isn't it? Let's call that 15. So that's an 8-second time period, and the speed hasn't changed much. Maybe it's gone from 12 to 14. There you go, 12 to 14, which is a change of 2. So 2 divided by 8, which is a quarter. 0.25 ms to the minus 2. You need to know how to write the units of acceleration, which we talked about already. Acceptable ways of doing it. You can write meters slash s squared. That is acceptable. Meters per second squared. Or you can write ms to the minus 2. That's also totally acceptable. What you cannot do, and is totally unforgivable, is something like that. You certainly can't do that. Meters per s to the minus 2. That's a no-no. Okay? I suggest, because you're doing grown-up physics, you should be doing that. ms to the minus 2. Okay, so in the book, there's quite a few pages talking about spreadsheet modelling of distance, time, acceleration, everything really. I like spreadsheet modelling. I think it's really important, and I am going to spend some time in a forthcoming video going through how to set up a spreadsheet model for you. Now, I used to work a lot on Excel, but I appreciate that Excel's not used by a lot of students because it's expensive and it's not on everyone's machine, and also it's not really built for sharing and caring, whereas Google Sheets is. And Google Sheets is free and everyone can have it. The functionality isn't quite as super duper as Excel, but it's not bad at all. And I'll show you how to do some very nice graphs using Google Sheets. We'll save that for a special lesson in a few months. Okay, moving on. Okay, we're now doing practice question 9, a nice easy peasy multiple choice question. The graph is much easier to read in the book than on my whiteboard here. And the question is, what is the best estimate of the distance travelled by the bicycle during the first 5 seconds? It's asking for an estimate. There is no correct, true answer. So 5 seconds actually is sort of more like there, but that's fine. All we have to do is to estimate the area under the graph, because it's a velocity time graph. Do you agree? Meow. Not very good. Do you agree that if I drew a straight line from 0 up to the line at 5 seconds, then the area of this triangle would be 8 times 5 times a half. 8 times 5 times a half is 20 metres. And we still haven't counted this much here. Now, if you look at the choices for the answers, we've got 15, 20, 30 and 40. Well, it's not 15 because it's definitely more than 20. And it's not 20 because it's definitely more than 20. And it's not 40 because in order to be 40, the line would have had to have been straight across from 8. So it's not 40. So the best estimate would obviously be 30 metres. So the answer is 30, which in the question is C. Are we all cool with that? Okay, so PQ10 follows on from the same graph and asks what is an estimate of the instantaneous acceleration at 2 seconds. So we go up to 2 seconds on the graph, which is about there, and we draw ourselves a tangent and we work out the gradient of the tangent. And I mean, this is completely rubbish because I've just sketched this, but anyway, I'll come up with a number. What is that? Well, if that's 1 and that's 8, the rise is 7. That's 0. Yeah, that's about 4. Something like 7 over 4. 7 divided by 4, which is about 1 3/4. And their choices are 1, 2, 3 and 6. So the one that's closest would be 2 metres per second per second. 2 ms to the minus 2. That's what I reckon. Okay, so we're now going to have a look at PQ11. There's a speed time graph of a sprint runner. Basically, it accelerates fast, levels off. We aren't given any values for speed, but we are given some values for time in seconds. And it's a multiple choice question about what's going on here at 4 seconds. And it basically gives choices. Instantaneous speed at 4 seconds. Do you agree that the speed there is the highest of any of the speeds during that time? And do you agree that the average speed for the first 5 seconds, for example, is going to be slightly lower because you've got this speeding up time over here? So when it says instantaneous speed at 4, it's going to be greater than the average speed. So it's going to be A or C. What's the instantaneous acceleration at 4 seconds? Well, the line is completely flat, so it's 0. So the answer is A. Okay, so we're going to have a go at practice question 12. This is a velocity time graph for a cart travelling in a straight line. We're going to talk about giving velocity positive and negative values probably next lesson. But do you agree, according to this graph, the velocity is negative? Now, the way I would read this is if you think about it going along a straight line, generally speaking, for most carts going along a straight line, the direction in which the cart is setting off is usually positive. So I suppose what we could do is say that this is the cart setting off along, and that this is positive. Going down is positive and going up is negative. It doesn't matter, but that would be logical because most things travel in the same in a direction, and we like to think of it going from left to right. So this is positive velocity. So it speeds up and then slows down. And at that point there, it changes direction, and it's now coming back with negative. It goes faster and faster in the negative direction, and then it slows down, and then it goes in the same direction as it was originally. The question is, how many times does the cart change its direction of motion? We are not told about what's going on before time 0, so we're starting from there. So we're looking at the number of times it crosses the axis. 1, 2. And the answer is twice. Okay, so here we have, for PQ13, we've got a very interesting velocity time graph, and it wants us to describe the motion of the cart during the first 2.5 seconds. Let's explain what's going on. The cart is going uphill to start with. It starts at 2 meters per second, going uphill. It's a cart. In physics, none of these things have got engines. They're going up the hill, but gravity is pulling them back down again. So it's slowing down due to the acceleration of gravity. Now, because it's on a ramp and it's not a rock being thrown over a cliff, it won't slow down as fast, or it won't change speed as fast as it would if I threw it up in the air. So it's slowing down from the moment it leaves until it reaches a point up the ramp where it comes to a stop. According to the graph, that's after 1.5 seconds. So it goes up for 1.5 seconds, and then it starts rolling back down. And because the line on the graph is completely straight, we know that acceleration is constant, which is a good thing because it's meant to be constant for our Suvat equations that we're going to be doing next video. So what do we say to fully describe this? Well, we can say that it left doing 2 meters per second and it started slowing down. We could work out the acceleration. Why don't we work out the acceleration? They love that stuff. Minus 2 divided by 1.5. Which is, not a very nice number, minus 1 1/3. So the acceleration is minus 1.33 ms to the minus 2. That is the constant negative acceleration. And we could also work out how far up the ramp it went, because the distance up the ramp is this area here under a velocity time graph. So that's 2 times 1.5, which is 3 times a half. So it's gone up 1.5 meters up the ramp, stops, and then rolls back down. And because it's completely frictionless, we know that the time it takes for it to go up the ramp will be exactly the same as the time it takes to come back down the ramp. What else do we know? Well, we also know that if we had the graph extended out to 3 seconds, the size of that triangle would exactly match the size of that triangle if we took it out to 3 seconds, because after 3 seconds it would come back to exactly where it started, but that's not shown on the graph. Okay, so I want to finish off video number 4 by looking again at constant acceleration in one dimension and what it means in real terms. Now, the most common constant acceleration in all physics questions is that you'll find with projectiles and things being thrown in the air. A thing that is thrown in the air in physics land only has one force acting on it, and that force is its weight pulling it back down. And because we are close to the surface of the Earth, we assume that the force acting, the weight of the object, does not change during its throw up into the air and back down again, which is a fine, that's a good assumption to make. What does this mean? It means that if I throw a ball up in the air at 8 meters per second, it will go up and come back down. And when it comes back down at the same point, it will be doing the same speed in an opposite direction, or if you like, the same value of velocity, but with the sign reversed. So if we say that up is positive, and spoiler alert, for all projectile questions, I always work with up being the positive direction. So when it leaves, it's doing +8. When it comes back, it's doing -8. What does this also mean? This also means that it doesn't actually matter. This is another interesting one. If I said to you, which situation will the ball hit the ground faster? Situation 1, I throw the ball up at 8 meters per second. It goes up and then comes down and hits the ground at the bottom of a cliff there. So situation A, I've thrown the ball up, it's gone like this and come back down, hits the ball, hits there. Or situation B, I throw the ball down at 8 and it hits the bottom. Obviously, the total time in A will be longer because it's had to go up and come back down again. But the actual velocity of impact at the bottom, the speed of impact at the bottom, is exactly the same. Because when this ball comes back down, it will be doing 8 meters per second going down. If and only if we ignore air resistance. Let me do one more example. So, to go back to more about the rules of things going in the air. On Earth, if you fire an assault rifle at, say, a muzzle velocity of, say, 400 meters per second, straight up in the air resistance will act as well as weight pulling it back, and it will go up maybe 4 kilometers in the air, 4,000 meters. Bullet will turn around and come back down. But on the way down, because of air resistance, it will reach terminal velocity and it will hit you on the head, probably traveling at about 60 or 70 meters per second. And it will hurt you. It hits you on the head, but it won't kill you. If we do the same thing with no air, it'll go up at 400 meters per second. It will go up an enormous distance. It will turn around and come back. And when it comes back, it'll be doing 400 meters a second again. So if you fire a gun on the moon, the bullet will go way, way up, maybe 100 kilometers, come back down. And when it comes back down, it's traveling at the same speed, but in the opposite direction that it left the gun. Now that's physics land for you, because in physics we are not going to have air resistance, so this applies. So you need to be aware of this. And this means that the time taken to go up is equal to the time taken to come down for a projectile. Always. The time taken to go to the top of the flight and the time taken to come back down to the same vertical position is always the same. And the vertical speed, when it left, will always equal the vertical speed by reversed when it gets back to the same point. I hope that's all clear. This marks the end of video 4, and in video 5 we're going to be looking at the graphical approach to explaining the 5 equations of motion. Ignore the book with its 4. The 5 equations of motion. So I'll see you again for number 5 shortly. Thank you very much.